All right, welcome. Today, we are going to crack open a classic programming puzzle called combination sum. Now, I know it might sound a little intimidating, but trust me, once you see the core idea, you'll realize it's built on something surprisingly simple and, honestly, really elegant.
So before we even touch the problem, let's just think about this for a second. How does a machine, a computer, find every single possible answer to a puzzle? It can't use intuition or have a lucky guess. It needs a system, a foolproof method to explore every single path so it doesn't miss anything. And that's exactly what we're going to map out today.
Okay, so here's the mission, plain and simple. We get a list of numbers, and here's a key rule. We can use each number as many times as we want. Our job is to find all the unique groups of those numbers that add up perfectly to some target value.
Let's make this way more concrete. Imagine our numbers are 2, 3, 6, and 7, and our target is 7. Well, there are a couple of ways to do this, right? You could take 2 2s and a 3. That adds up to 7. Or you could just grab the 7 all by itself. Our goal is to create a process that can find both of those solutions automatically, every time.
So how in the world do we do that? Well, the magic key, the one big idea that just unlocks this entire thing, is a concept called pick or don't pick. It's this beautiful way of taking a kind of messy problem and boiling it all down to one single repeatable decision.
Yeah, that's literally it. We're going to look at each number in our list one by one, and for each number, we're just going to ask ourselves a super simple yes or no question. Do we pick it and include it in our potential answer, or do we don't pick it and just move on?
So let's break down those two choices. If we go down the pick path, we add that number to our current combo, and, this is important, we stay on that same number to see if we want to pick it again. But if we go down the don't pick path, we just leave everything as is and move on to the next number in the list. By exploring both of these paths for every number, we end up building this massive decision tree that guarantees we find everything.
Okay, theory is one thing, but seeing it in action is so much better. Let's actually walk through the exact steps our little process would take to find that first solution we talked about, the combination of 2, 2, 3.
All right, here we are, right at the beginning. We've got our list of candidates. Our target is 7, and the very first number we're looking at is the 2. So, we have our choice to make. Do we pick it, or do we not pick it?
Okay, for this walkthrough, let's follow the pick path. We're going to take the 2. The moment we do that, two things happen. We add that 2 to our current combination, and we subtract its value from our target. So our new target is 7 minus 2, which is 5.
Now remember that crucial rule, we can reuse numbers. So we don't move on to the 3 yet. We stay right here on the 2 and ask the question again, should we pick 2? And you know what? Let's say yes again. So our combo becomes 2, 2, and our target shrinks again, down to 3. Okay, we're still looking at the number 2, but this time let's finally make the other choice. We say don't pick. What does that mean? It means we're done with the number 2 for this specific path, and we finally move on to the next candidate in our list, the number 3. So check this out. Look where we are. Our combination so far is 2, 2. We're now looking at the number 3, and our target is also 3. This feels pretty good, right? So we have to decide, do we pick the 3 or not? We make the obvious choice and we pick the 3. We add it to our combination and our target becomes 3 minus 3, which is 0. And that, a target of 0, that's our signal for success. That's the finish line. We've done it. We've found a valid combination, 2, 2, 3.
Okay, so we found one answer. Awesome. But what about the other solution, the 7? This is where this really clever idea called backtracking comes in. It sounds fancy, but it just means the process hits rewind. It mentally goes back to the last choice it made, and this time, it explores the other path. It unpicks the 3, then it unpicks the 2, and it just keeps doing this until every single possible path has been explored.
So that manual walkthrough gives us the gut feeling for how this works. Now, let's formalize it. Let's turn that journey into a repeatable blueprint, an algorithm that a computer can follow without us holding its hand.
So, whenever you have a process that calls itself over and over again, which is what we're doing, you absolutely need an exit strategy. In programming, these are called base cases. They're just the simple, non-negotiable stop signs that tell the process, hey, this particular path is over, stop here.
For our process, we need 3 of these stop signs. The first one is the happy path. The target hits exactly 0. We found a solution, we save it, and we stop this path. The other 2 are dead ends. If the target ever becomes a negative number, Well, that path is busted, so we stop. And finally, if we just plain run out of numbers to check, that path is also a dead end. We stop. And this is the engine that drives the whole thing. The pick action reduces our target and then runs the whole process again on the exact same number. But the don't pick action leaves the target alone and tells the process to move to the next number in the list. That dance between those two calls is what explores everything. Now for the really cool part. Let's see how that clean, simple blueprint we just designed translates almost one-to-one into the actual structure of a computer program. And you really don't need to be a coder to see how the logic fits together. This table right here, this is the whole engine in a nutshell. Every single decision comes down to this. We either pick the number, which shrinks the target but keeps us on the same number for the next choice, or we don't pick it, which leaves the target alone but moves us to the next number. That is the entire recursive dance right there.
And that's really the power of this approach. It's not random. It's not based on luck or some clever insight. This simple pattern of pick and don't pick, when you apply it over and over, creates a totally exhaustive search. It methodically checks every single branch of that decision tree, which guarantees we will not miss a single valid answer.
So why does all this matter beyond just this one puzzle? Because this right here is a fundamental strategy for solving problems not just in computer science, but, well, anywhere. Taking a huge, intimidating challenge and figuring out how to break it down into one tiny, simple decision that you can just repeat. That is one of the most powerful tools you can have. And that brings us to our final thought for today. We built our entire logic around the rule that we could reuse numbers. But what if you couldn't? What if you were only allowed to use each number in the list one time? How would you change that simple pick step in our blueprint to handle that new rule? It's a small change, but it makes a big difference. Something to think about. Thanks for tuning in.